Okay, hello. So this is the additional video for the Chapter 4 presentation for CCNA1. And so in the lecture we finished with this slide as properties of wireless media. So to recap, wireless media carry electromagnetic signals that represent the binary digits of data communications using radio or microwave frequencies. So wireless areas of concern is the coverage area. So that can both be good and bad, and so if the building is made of thicker material, it may actually restrict the coverage area. But of course, another problem can be that you've got too much coverage area, and so other people can snoop onto your signals. So interference, of course, is something else that affects wireless media. So there are fluorescent lights, microwave ovens, other wireless communication devices that can all disrupt the signal going through, and of course interrupt your network communications. Security, as I said, the coverage area, if it's too big, other people who are not authorized can snoop on your messages. I'm going to say encryption does certainly help with that, but no encryption system is perfect. And of course, the last problem with it is that it's a shared medium. So everyone connected to your wireless network are sharing the bandwidth of to talk to the access point, basically. Oops. Thank you. So the types of wireless media, it's basically what, different types of wireless communications. So by far the most common one is Wi-Fi or 802.11, and so it uses a carrier sense multiple access collision avoidance system to control who has access to transmitting at any one time. And so that basically means that the wireless NIC must wait till the channel is clear, and then it asks if it may transmit. That's the collision avoidance. Bluetooth, of course, is more a personal area network, and so with that, more often than not, it's just output to speakers or headsets or whatever it might be with those. You don't often do network communications with it. You can, but not often. And then WiMAX is actually sort of a longer distance solution compared to 802.11, and so typically it is a point-to-point wireless link, and so there's a fixed antenna on a central building somewhere, and then other buildings have their dish pointing at that antenna, and that's how they connect to the network. And so it's more of a fixed broadband solution that uses wireless. So, of course, many home and small business wireless routers integrate the functions of a router, switch, and access point all into one device. And so most of you in your home networks will have such a device. And so wireless LAN requires that you have a wireless access point. And so that's your centralized router that uses wireless antennas for the wireless signals. And so it connects your wireless network to typically a copper-based network to connect to the rest of the world. And of course, to connect to that wireless network or access point, you need to have a wireless NIC adapter inside your device that you're trying to connect to it with. So most modern phones and tablets and all that will have wireless NICs, as will laptops. Other devices, you may actually need to add a wireless NIC. So what data link protocols are these? And so we've been mostly talking about the physical layer up until now, and so the data link layer is all about moving the frames across a segment, and so it's all about getting that frame reliably from the source machine to the destination machine on the segment. And so to do that, that's when we use the destination and source MAC addresses in the layer 2 header, and that's just identifies who sent it and who needs to receive it. And so from that, either the wireless access point or the switch will normally forward it towards the intended destination. And so the data link layer, of course, is layer 2, and the IEEE has divided the data link layer into sub-layers. And so the logical link control LLC layer is basically the one that has all the procedures that are consistent between all the different layer 2 protocols. They are all bunched in together, so they only have to do it once basically. And so it's of course what takes care of, because it's higher, it takes care of communicating with the network layer, and then it also, with the lower layer, of course, it talks to the MAC sublayer. And so that MAC sublayer is what's rewritten for each different technology, be that Ethernet or Wi-Fi or whatever it might be. And so it provides the, well, it interfaces more directly with the hardware, and it does your data link layer addressing and access to various network technologies. So communicates with the Ethernet to send and receive frames over copper or fiber optic, and it does wireless for Wi-Fi and Bluetooth. So with media access control, it's all about controlling which host gets to transmit their data at any one time. And so different data link layer protocols use a different process for deciding that. So as packets travel from the source host to the destination host, they travel over different physical networks. Physical networks can consist of different types of physical media, such as copper wires, fiber optic cables, wireless consisting of electromagnetic signals, or satellite links, which of course is another wireless setup. At each hop along the path, an intermediary device accepts frames from one medium, de-encapsulates the frame, then forwards the packet with a new frame header. The headers from each frame are formatted for that specific media as it goes. So as you can see here, this is Ethernet. I'm assuming that must be fiber optic. Then you've got a satellite link, another fiber optic, and then you've got Wi-Fi here. And so each of those will have a different frame header on layer 2, basically, for each step along the way. So, as the name suggests, media access control provides access to the media. And so each hop along the path, the router accepts a frame from a medium, decapsulates the frame, re-encapsulates the frame onto a new one, and then forwards that frame onto the medium for the next hop, basically. And so its header will change between this LAN segment and this WAN connection. So data link layer standards mostly come from the IEEE, ANSI, ITU, and ISO. And so again, we have covered the standards organisations previously, but again, it's fairly low. So when it comes to LANs, IEEE is your driving force. When it comes to WANs, probably ITO is where you get more of it from. So media access control. Basically, as the diagram suggests, we need rules for how to share the media, and so all devices hooking into an Ethernet network need to use the Ethernet method of deciding who gets to transmit. So media access control is the equivalent of traffic rules that regulate the entrance of motor vehicles onto a roadway. The absence of any media access control will be the equivalent of vehicles ignoring all other traffic and entering the road without regard to other vehicles. However, not all roads and entrances are the same. Traffic can enter the road by merging, by waiting for its turn at a stop sign, or by obeying signal lights. A driver follows a different set of rules for each type of entrance. So when it comes to topologies, there's two major types of topologies for organising networks, and so there's the physical topology and there's a logical topology. So at the moment we're looking at a more physical topology, and so it refers to your physical connections and identifies how end devices, infrastructure devices, such as routers and switches and wireless access points are connected. And so you'll see a one-to-one relationship between cables and where they run through a building or whatever. While a logical diagram is a little more about how the network is organized, how the hosts are grouped and things like that. So who belongs to what network, and that does not necessarily have all of the same hosts in the same network being in the same part of a building or something like that. That can be a little bit remote. And so basically these logical signal paths are defined by data link layer protocols. Now, common physical WAN topologies are point-to-point, hub and spoke, and mesh. So point-to-point is what a typical WAN link is between a branch office and a head office, and so just a point-to-point link. If you've got more than one branch office, then basically most branch offices would directly connect to the head office, this hub office, and so you end up with a hub and spoke. Now a mesh is where you actually have redundant links as well. This diagram to me looks like a full mesh in that there's a direct link between every node and every other node. And so it's wonderful. You have reliability, you have direct access, but every one of those links, on a WAN at least, you need to pay for it. And so it can get a bit expensive. So here, if one of these links dies, one of your sites is disconnected from the rest of the world. Here, well, then if that link died, it could just go there to there, or 4 other options, basically. So ultimate reliability, see you, mate. But of course more expensive. So you can actually sort of go between the full mesh and a partial mesh, where you might have these links and then maybe they also have a direct link between each branch office and 1 or 2 other branch offices, just to give you alternate methods of connecting. And that can give you some reliability if you have links failing. So point-to-point frames are placed on the media by the node at one end and of course accepted by the node at the other end. So it's just a point-to-point circuit basically. Most of those are leased lines, but they are other options. Now you can also have logical point-to-point topologies where basically you put your frames into the telco's cloud. They go via magic and end up at the destination node. So when nodes communicating in a point-to-point network can be physically connected via a number of intermediate devices. However, the use of physical devices on the network does not affect the logical topology. The logical connection between nodes forms what is called a virtual circuit. So basically you dump it on the telco's network and it goes through the cloud towards the destination. And so basically this is illustrating the point that was in the other one. If they add extra physical devices in the cloud, it's not really your problem as long as your data still gets through their cloud. Now, LAN topologies, there's several options for those. And so a star topology is basically what Ethernet does. The central point on that star topology is the Ethernet switch, and all hosts connect into it, and so they're organized in a star fashion. An extended star is basically where you hook 2 or more switches together, and so you have a star of stars, basically. Bus topology is an older setup, and so typically with the bus topology, you have a bus that goes past all the workstations. At each end there is a terminator, or basically it's just a resistor, and then all the workstations connect in using a T-piece to that bus. And so basically, so Ethernet bus networks were set up like this. There's also been local talk from Apple as well. They work in a similar fashion. The problem with them is they're an all or nothing network. Either the network works or it doesn't, and there's no sort of indication of where a fault might be. If you get a break in the network somewhere, instead of having a functioning network, you've actually now got 2 networks that will not function. And so everyone is disconnected. So if there was a break there, well, there's not a terminator at both ends of that now shorter segment. And so that won't work, and the same on this one. So nothing worked. At least with this, if a cable breaks, you lose a workstation. Oh, okay. That tells me that that workstation's cable has failed. So that all instantly gives you some information about where the break might be. And then there is also a ring topology, and so typically that ring was inside a box that looked quite a bit like an Ethernet switch as well. And so with that, the ring topology normally had a token, so that was called token ring, and the token would be passed from workstation to workstation to workstation. When they have the token, they can transmit. When they don't have the token, they cannot, and so there was only ever one station transmitting at a time. So token ring was the first one that did that. There was also FDDI, Fiber Distributed Data Interface, that does that as well. That was, token ring is a really old legacy setup. FDDI was one of the first fiber standards that was available. So still a little bit legacy. Now when you're transmitting data over a link, you've got the option of full duplex or half duplex basically. Now half duplex is where data can travel in both directions, but only one direction at a time. It's a bit like how the Southern Expressway was 10 years ago, where, you know, in the morning you could travel towards town, in the evening you could travel away from town, but not both at the same time. While full duplex is both directions at the same time, and so of course that means that there's greater capacity. It basically doubles the bandwidth that's available. And so for that to happen in Ethernet, you must have Ethernet switches for every host. Now, basically, if you had an Ethernet hub or an Ethernet bus, there was a contention-based access method where it was CSMA CD, which is carrier sense, multiple access collision detect. And so basically what happened there was, with Ethernet, there was no order in which people got to transmit. It was just the first one who needed to started, and then everyone else would have to wait until they're finished. So that's the carrier sense. If no one else is using the network, hey, I can use it, which is carrier sense is listen to the network, multiple access is use the network. But of course, two hosts might decide at the same time that they wish to transmit, and then you can have a collision, and so then hosts need to be able to detect that collision and then recover from it. And so that's the CD, collision detection. With a token ring, as I said, everyone has their turn, and so as they when the token comes around, they can transmit, and so that there was never any collisions with that. So as I said, CSMA CD, if two devices transmit at the same time, a collision will occur. Both devices will detect that collision because they will modify each other's signals. Data sent by both devices will be corrupted and will need to be resent. And so basically when that happens, they both wait a random amount of time and then try to transmit again. And so hopefully they don't both decide on the same random amount of time. Wireless, as we said, is CSMA CA, so it works much the same as Ethernet, but the difference is it's a little more polite. Basically, a wireless workstation, if it sees that the wireless is not busy, will actually send a packet called, a frame called a request to send, and then the access point will say, yes, you are clear to send. And so it will only give one workstation permission to transmit at a time, and so there's a lot less chance of collisions, hence collision avoidance. So each frame type has three basic parts: a header, a data section, and a trailer. Different protocols organize these things a little differently. And so the structure of the frame and the fields contained in that header depend on a layer 3 protocol as well as the needs of the layer 2 protocol. If you have setups that are more susceptible to errors in transmission, then they actually have to have a higher overhead to get transmission to work properly, and so that will actually slow down the transmission. So frame fields, so of course frame is your layer 2 data protocol unit, and so this is, you have your header, your data, and your trailer, as it said. The data section, of course, is typically variably sized, but of course the header and the trailers have their different information. So most protocol systems will have a frame start field of some sort, and then they may or may not have addressing depending on what type of link it's going across. It'll have type of field and other control messages. Normally most layer 2 protocols will have a error detection section or frame check sequence at the end, and so that will basically do a calculation on the first part of the frame, store the result there. When it arrives at its destination, the destination will do the same calculation on the same part of the frame and compare results. If it's the same result, the data hasn't been somehow modified in transit, and so there's no errors. Now, not all layer 2 protocols have a frame stop field. Some might actually have a field in there telling you the frame length, but yeah, many of them do have a frame stop field though. So layer 2 addresses. On a multi-access network like Ethernet, you certainly need MAC addresses to address towards the destination host. On point-to-point networks, you don't actually need to have a layer 2 address because there's only 2 hosts on it, and yeah, If it's not me, it's the other one. So it's, if you're sending it in one direction, well, it must be destined for the other end. So it's normally just your multi-access networks that have layer 2 addresses. Okay, so LAN and WAN frames. Basically, more of your LAN frames will have addressing fields in them, but of course it does vary on their need. While the WAN links like point-to-point protocol, HDLC and frame relay often will not. Point-to-point, triple P and HDSL do not. Frame relay does, but they're more of a virtual circuit number than anything really. Okay, and so there are some activities for this chapter, or chapters, but they are more conceptual chapters, so there's only one per chapter. And so the summary is we explain how physical layer protocols and services support communications across data networks, and we build a simple network using the appropriate media. Explain the role of the data link layer in supporting communications across data networks. We also compared media access control techniques and logical topologies used in networks. So that was the end of chapter 4. So there's the logo, and so I'll catch up with you again next week with chapters 5 and 6. I'll see you then.